on guztioi eta ongi etorriak izan zaitezte, zientziaz eta teknologiaz berbetan 2024ko udazkeneko jardunaldien bigarren hitzaldira. Eta esan beharra dago, hirugarren aie martxan dagoela, datorren astean izango dela, azaroaren 6ean, eta bere izenburuare emango dizuet, The Amazing Story of Lactate, Key to Understanding Cellular Metabolism in Health and Disease, eta hitzaldi emalea izango da Estatu Batuetako George Bruce ikerlari aipatu arlo honetan, eta gainera kasu honetan egingo dugu hitzaldia batera EH foroarekin, eta pertsona honi sari bat emango zaio, eta izango da atletikoko medikutza zuzendarietatik emango diote, zeren lan asko egin du arlo horretan, kirolari mota guztiekin. Eta gaur daukagun hitzaldia, Thomas Stockerrek emango du, eta bera aurkezteko hitza emango diot, Santi González fisika saileko irakaslea da. Hau da, Zientzia eta Teknologia fakultateko irakaslea. Sartu.
Bueno, pues hola a todos. Y eso, como ya ha dicho Fernando, el ponente de hoy es Thomas Stocker. Y por si no lo sabéis, pues él obtuvo su doctorado en la Universidad de Zurich, ¿vale? Y tras realizar el doctorado en la Universidad de Zurich, pues ha investigado en sitios como Londres, Montreal, Nueva York y Honolulu. Y tras realizar estos postdocs, pues decidió, obtuvo una plaza de profesor en la Universidad de Bern. Esto en 1993. Y tras esto, hasta el 2024, ha llegado a ser catedrático y director de la División de Clima y Ciencias Medioambientales de la Universidad de Bern. Y desde este verano es profesor emérito en la Universidad de Bern. Y yo he tenido la oportunidad de trabajar con él durante los últimos 5 años y medio también en la Universidad de Bern. Fernando no lo ha dicho, pero en junio recibió el premio BBVA a las fronteras del conocimiento por su trabajo en Antártida y el análisis de los ice cores, ¿vale? Y además de eso, pues tiene una trayectoria bastante importante de premios, que voy a leer. Es doctor honoris causa de la Universidad de Versailles y la Escuela Politécnica Federal de Zúrich. Obtuvo el título de mejor tesis doctoral de la Universidad de Zúrich, de la Universidad Politécnica de Zúrich. Obtuvo el premio Descartes de la Comisión Europea, el premio Latsis del Swiss National Science Foundation, la medalla Hans Osger de la Unión Europea de Geociencias, el premio Emiliani Lectures de la Unión Americana de Geociencias y Premio Nacional de Ciencia de Suiza y Bélgica. ¿Vale? Esto durante toda la investigación de Thomas. Y aún así, lo más importante o lo más remarcable es que entre 2008 y 2015 también ha sido copresidente del IPCC, que es el Grupo Intergubernamental de Expertos del Cambio Climático. ¿Vale? Y esto es algo importante, puesto que esa base científica que desarrolló en conjunto con otros investigadores, pues ha sido la base científica utilizada para el Acuerdo de París. Y como detalle, decir que el último informe de evaluación, el quinto informe de evaluación lleva su nombre, se cita con su nombre y, oye, mirad, y en Scholar, you have 9,800 citations of this report. Es decir, que tiene casi 10.000 citas del informe de la R5. Y eso, es un honor tenerla aquí y hoy nos va a hablar sobre Climate Physics, Models of Early Warning Systems in the Climate Crisis. Así que nada, esto es todo. Thomas, the floor is yours.
Well, thank you very much for this kind introduction. And these young professors, they cannot follow the advice of elderly professors, because I told him not to tell all these awards and prizes. That's not really interesting. Interesting is more how much you can do in an academic career, how many interesting people you meet and you can collaborate with. Santos is one of them, but there are many others. And the most important thing is that we can all work with the next generation of decision makers. You are the next generation of decision makers. And so if you are in that position, you need the science that informs you, and not fake news and other things that you can see on TikTok, etc. Scientific results. And in the topic of climate change or anthropogenic human-made climate change, scientific information is key to take the important and correct decisions. So in that context, I would like to talk about what we know in climate science and take you through a journey of the last 60 years of climate science with some very up-to-date information that tell us about this climate crisis. Let's look at the most important time series in the discussion of climate change. I'm sure you have seen this data before. It's the Keeling curve in the name of Charles David Keeling, a US researcher that started in the 1950s with one goal in his life: to carry out the best and most precise carbon dioxide measurements in the atmosphere. And he succeeded. As you see here, the time series starts in 1958, shows the evolution of the concentration of carbon dioxide, the most important greenhouse gas in the atmosphere after water vapor. And it shows two things. One is a monotonous increase over the last 60 years, and the other one, this is the seasonal cycle, the breathing of the carbon dioxide to build the organic material. In fall, it's shedding the leaves again, and carbon dioxide concentration slightly increases. And that causes these little, but the wiggles are also a message that these measurements are extremely precise. So you can trust also that increase that you see from 1958 to 2024. We're now over here, 35% higher since 1958, the beginning of these measurements, and in fact, 54% higher since 1750 being the year where the Industrial Revolution started, where people started to use machines burning coal, and then later on fossil fuel. Since 1750. And of course, the first question that science was asked in the early days was, oh, how can you be sure that this is not just a natural fluctuation? It's going up and down and up and down. And all we see in the last 60 years is perhaps just a quarter of a sine wave. That's a very valid question. But you can guess who asked these questions. Those who didn't believe the scientists in the 1950s, who already knew at that time that this increase is unprecedented and was caused by the burning of fossil fuels. And in order to actually prove that this is unprecedented, you have to go back in time. But of course, there weren't any measurement stations before 1958, so we have to inquire nature to give us that measurement system. And fortunately, past greenhouse gas concentrations are stored on this planet. They are stored in ice cores, and that is a time series over the last 800,000 years of carbon dioxide concentration, measured on tiny air bubbles in ice cores from Antarctica. So at our university, we're specialized in carrying out these measurements, going to Antarctica, as was mentioned, drilling down 3 kilometers into the ice, going back 800,000 years. And what you see here is the result of many, many hours, days, and years of research to finally present this unique time series of carbon dioxide concentration, natural variations that start 800,000 years before the present, going through 8 full glacial cycles, to 20,000 years before the present, where we have low concentrations on the order of 180 ppm, and then up to 320 ppm at the beginning of the 20th century, and today we are here. So there are natural fluctuations in the climate system of this important greenhouse gas, but they are far outpowered by the increase over the last 250 years caused by human activity. And so we now turn a little bit to physics. What does that mean if the greenhouse gas concentrations on the planet Earth increase in the atmosphere? And for that, I show you the simplest possible climate model that I can think of. It's a so-called planetary energy balance. So it's satisfying just one equation, and that's the equation of energy balance. No movement, no fluid motion, nothing, just the energy balance. And you see here this planet here, you see 2 types of arrows, the shortwave radiation that we receive from the sun with the solar constant S sub 0, and the long-wave radiation that follows Planck's law with an emissivity epsilon. And the climate model says nothing else than these 2 things in equilibrium must be in balance, and you can write that down as a left term that shows the rate of change of the temperature of the planet, the mean temperature of the planet with some heat capacity and density of the atmospheric air, and the incoming radiation here reduced by the reflectivity, and the outgoing radiation here modified by emissivity. That's all. That's the energy balance of the planet. And now we have to think a little bit about what a greenhouse gas molecule does in the atmosphere. It actually is a molecule, and that's told by quantum mechanics. Carbon dioxide and water are molecules that are able to absorb infrared radiation. They absorb this energy by vibration and rotational motion, and then give off that radiation again into a random direction. So what comes in as a directive energy flux is then radiated away in the space angle 4 pi. And so if you look from outside to the Earth in the visible range of wavelengths from 400 to 700 nanometers, that's sort of the typical blue marble that you all know. In some stages, you can actually see right down to the surface. Here, you can see right down to the surface, the southern part of the African continent, and in other parts, the view is obscured or blocked. Here by clouds, part of the water vapor, of course, but a very specific part. And so the important point of the question is, how far down can we see to the Earth's surface in certain wavelength bands? If you look at the Earth in the wavelength band from 8 to 12 micrometers, which is the infrared band, in which water, carbon dioxide, and methane absorb, then that's how planet Earth looks like. You can no longer see continental outlines. So your view, your line of view is blocked at some altitude in the atmosphere. It's like if you look into a contaminated lake. If the lake is pure, you see down to the ground. If the lake is turbid or contaminated or full of dust or whatever, you just don't see to the ground. And that's the very same effect. Your line of view is blocked. And now let's look at that, because in the end, we will understand how the greenhouse effect will work in the atmosphere. So what I show here is a diagram of temperature and altitude in the atmosphere. We go from the surface, 0 kilometer, to 10 kilometers. And you all know if you go higher up, hiking in the mountains, it's a bit fresher. So you have a natural temperature gradient of about 6.5 degrees Celsius per kilometer. So 1 kilometer above is about 6 degrees colder than at the surface. That's just the adiabatic equilibrium of
the atmosphere. Very well understood, a very stable relationship. Now, if we look at the Earth without greenhouse gases from above, from space, our line of view comes from the outside and goes right down to the bottom. No obstacle, nothing. If, however, we have greenhouse gases, our line of view or depth of infrared visibility is reduced, and it's reduced to the depth of about 5.1 kilometer. We can't see further down. And the temperature at 5.1 kilometers happens to be minus 18.6 degrees Celsius. And if you now inquire Planck's law of radiation, that exactly amounts to 238 watts per square meter lost to space. That's exactly the value that we get from the sun in the form of shortwave radiation. So the planet is in energy balance, and the effective radiation temperature is minus 18 degrees Celsius. So you ask, well, why is the global mean surface temperature plus 14 degrees? Well, that's thanks to the greenhouse gases, water vapor, carbon dioxide, methane. So greenhouse gases are something good. Without greenhouse gases, we wouldn't be able to have life on planet Earth. But greenhouse gases are trace substances in the atmosphere. They're only very low concentrations. And that's why we have to be concerned. Because look what happens if we increase the concentration of greenhouse gases. For example, just as a thought experiment, to 2 times pre-industrial concentration. We're not there yet, but we're on a good track to get there. 2 times CO2. Well, what happens is when we are at 2 times CO2, we can even less see the surface of the Earth. So the line of visibility is even shorter than before, which means that this line moves up, and because it moves up through a vertical temperature gradient, the temperature there is colder, about minus 21.6 degrees. That is about 3 degrees colder. And here we have only 230 watts per square meter, not the 238 watts per square meter. So what does that mean? It means that the Earth loses less radiative energy to space, which means it must heat up because it loses less than before, and it heats up exactly so much, and this atmospheric volume below 5.6 kilometers, that in the end, once equilibrium is achieved again, we have again minus 18.6 degrees Celsius and again 338 watts per square meter. That's the greenhouse effect. Okay. No greenhouse layer or something, but it's just a matter of understanding that radiative flux as it goes through a higher level. Now, because the adiabatic stable atmospheric column is such a strong constraint, that will not change, and you can have that same structure of the atmosphere if you just heat up the entire troposphere. And that's indicated here in this picture. Now, based on that understanding of a heating of the entire troposphere by about 3 degrees Celsius, we ask the question, what happens in the stratosphere? There must happen something there. And if we look at what people knew about the stratospheric temperature, that's about the sort of the temperature profile through the first 40 kilometers of the atmosphere. The usual reduction of temperature, then a layer of about 10 kilometers with uniform temperature, and then temperatures actually increase, okay? And that increase in the stratosphere is typical because you have ozone there and other substances that provide the heating. But if we now increase our greenhouse gases, the stratosphere actually shows a different behavior because the increase of the effective radiation layer now leads to a higher temperature. That is more radiative energy loss, and that means a cooling in the stratosphere. And so you have this interesting behavior that the troposphere warms, the stratosphere cools, and that itself is a fingerprint of the effect of an increase of greenhouse gas concentrations. These two things, it's not just the warming of the surface, which everybody refers to, but the vertical fingerprint that is such an important indicator that what we see today is caused by the increase of greenhouse gases and not by, say, changes in solar radiation. And in fact, that's what we see in measurements, and these are figures from the IPCC report, the last one in 2021. On the left, you see the temperature profile through from 70 south to 70 north in a zonal average, and you see very clearly from 2002 to 2019, you see essentially below 15-kilometer warming, above 15-kilometer cooling. The same thing from satellite measurements here, radio occultation measurements, a cooling up here and a warming down here. Exactly as this very basic consideration of the greenhouse effect has predicted. And this is also simulated in models. If you look here at a projection that was carried out in the climate modeling experiment CMIP5 for the fifth assessment report, already more than 10 years ago, you see very clearly in a similar graphical representation, big warming below 200 millibars and cooling above. So models and the fundamental physical understanding how the atmosphere works actually agree. Now we turn back to our energy balance model, and I just repeat that equation, and I generalize it. So left, it looks like the rate of change of the global mean temperature is caused by three different terms, plus a fourth term here, a delta Q, and that's the anthropogenic or human-made perturbation, for instance, the increase in greenhouse gas concentrations. Now, if we linearize that, that's an exercise that everybody of you can do, just plug that into the differential equation, and out comes a perturbation equation for that temperature, T wiggle, equals a source term that is proportional to the perturbed temperature plus this radiative forcing, we call it. And these three different terms are sensitivities or feedback parameters. They measure how a process reacts to the increase in temperature. Process A, B, C, how does it react to a temperature change? And in fact, you can also add here the total by just adding these lambdas A, B, C together. And you can inquire then all climate models today, how big this total is. You see it at the right side. There are different processes here, water vapor, surface albedo, net cloud. We don't go into that, but the total here is somewhere between 1 and 2 minus watts per square meter and Kelvin. In fact, minus 1.2 watts per square meter and Kelvin. Now we take that value, plug it in here, solve it for, it's a very easy solution here. You can almost do it in your head, and you come up with the equilibrium warming at 2 times CO2. So the only thing we need to know is how many watts per square meter per increase in carbon dioxide concentration. That's something that we get from different research. And we know that here we have about 3.7 watts per square meter. Plug that in, divide through 1.2, take the minus away, and you get the delta T. And what comes out? Well, 3.1 Kelvin. That's just about what we had before. So for every doubling of carbon dioxide, we get an increase in temperature of 3 degrees Celsius. We're not yet there. cool down. We are at 1.2 degrees Celsius. But global mean, only in the last 50 years, 1.2. Now, IPCC, which is this Intergovernmental Panel on Climate Change, has assessed since 1990 what we know scientifically about climate change, both past, present, and future. And one of the key quantities to characterize the response of the atmosphere to a change in greenhouse gas concentrations is this equilibrium climate sensitivity. And you see these estimates from different models here from 10 years ago and from a couple of years ago all over the place. In fact, the spread has become bigger, which was really a concern to the scientific community. But we have nevertheless come to a consensus. Some of these values here are unrealistic, and we know why. We can pinpoint to the cause in these models why these sensitivities are so big. And if you look at this more carefully, in 2013, we said it's likely to be 1.5 and 4.5. And in 2021, that range became very likely, that is more than 95% sure, between 2 and 5 degrees Celsius. With a best estimate, lo and behold, 3 degrees Celsius. And that's the current status of knowledge. I hope that in the next assessment, which will be published in 2026 or 7, depending on how hard the scientists work, I hope that this range here, this very likely range, can be narrowed. We'll see. That brings me now to another thing that was remarkable 3 years ago. About this time, it was announced that the Nobel Prize in Physics would go to 3 individuals, Suki Manabe, Klaus Hasselmann, and Giorgio Parisi, for groundbreaking contributions to our understanding of complex physical systems. So it was not a Nobel Prize for some astrophysical discovery or particle physics or whatever. It was for understanding complex physical systems. And 2 of these laureates were actually climate scientists of the first generation, developing models. And I want to show you a few examples how physics in the early days contributed to our fundamental understanding. I start with Suki Manabe, who received it for physical modeling of the Earth's climate, quantifying variability, and reliably predicting climate change. This was the first key paper in 1967 on the thermal equilibrium of the atmosphere, given a distribution of relative humidity. And he looked at this question, what do greenhouse gases do? In fact, now we understand everything I'm going to say because I gave you already the explanation. In this paper from 1967, you have this graph here that shows the temperature profile, now simulated in a model, not just our little conceptual model, but a real model. For 300 ppm, that's the temperature profile up to 10 millibars of pressure, or about 40 kilometers. You see the cooling in the troposphere, where the temperature decreases with altitude, the more or less constant temperature in between, and the warming above. Now, his simulations for 600 ppm yielded this result, this temperature profile, where you see already this fingerprint I was talking about. That was one of the key works and papers that led to the recognition of the Nobel Prize in Physics many decades later. But he also worked on further making climate models much more realistic. This first model in 1967 was just a vertical model with one spatial dimension. This one here, with his colleague Kirk Bryan in 1969, they already published a 3-dimensional model of an idealized planet. Look at how idealized this planet is. One ocean, a little bit of land, some polar areas, but the whole world was just a 120-degree wedge of the planet. Why is that? because of computational constraints. In the early 60s, they couldn't really calculate an entire planet. That was out of reach of memory, reach of CPU. It wasn't available. So they sort of used a very clever setup. They then, 10 years later, already had continental outlines, topography. They already had an ocean, and you see how simplified these models were at the time. But they were clever enough not to overinterpret their scientific results. One result that impressed me really was the result published in 1989 that showed a simulation of a global model, atmosphere-ocean model, to track the temperature change as a function of geographical latitude. What you see here is a diagram from 0 to 100 years, from 90 south to 90 north. So essentially at every point in this diagram, you have a profile across the latitudes of temperature change at a given time. It's a so-called Hofmiller diagram, and you can see here the warming above 2 degrees Celsius stippled, and you see a clear pattern of so-called polar amplification. You see here the warming is first appearing pronounced in the northern hemisphere, north of about 45 degrees. That's where the biggest warming occurs, and the lowest warming occurs on the planet in the southern hemisphere between about 50 and 70 degrees south. The reason? Well, in the southern hemisphere, you have the ocean that takes up a lot of heat. Heat capacity high of water, heat capacity of soil much less, and therefore you have a larger delta T here than down here. Now, at the time, I asked my PhD student, Christian Wirz, could you actually look at measured data and produce me the same Hofmiller diagram? I wouldn't have been able. Within a day, he furnished this plot, and just compare these two plots. They look very, very similar. And so what was predicted in 1989, based on a model that from today's perspective is a poor model, a simple model, has actually materialized in over the 4 decades, as predicted by these climate models. Very nicely, you see the polar amplification, you see the massive heat uptake by the ocean in the southern hemisphere, so the southern hemisphere is warming much more slowly. Likewise, Klaus Hasselmann from the Max Planck Institute in Hamburg made important contributions as well in a different way. He constructed a climate model with which one could actually investigate climate change. Not make simulations for just 30 or 100 years, but simulate thousands of years. And that was based on a simplified form of equations. Here again, equations. They are really important. And so with that model, he could actually also model not only the physical world, but also the biogeochemical world, and address the question, what's happening to the carbon dioxide when we emit it in the atmosphere? How is it taken up by the ocean? How is it distributed on planet Earth? And one simulation that I found really compelling and intriguing was this one here, out of a work in 1987, just a few years before I started climate research. And so these two individuals were always a little bit my lightning rods and role models. So what they did, they simulated carbon-14, which is a radionuclide, a naturally occurring radionuclide, in the ocean, and made a prediction of the age of the water in the Pacific. And what you see here are a few stations where my predecessor of the University of Bern has measured the age of the Pacific water. And this model actually nicely reproduced these measurements that were already made in 1959. To determine how old is Pacific water, what they found out is that water is 1,000 years old. Hasn't seen the atmosphere in 1,000 years. And that's a result that has to do with the global ocean circulation. Klaus Hasselmann also in 1993 presented a method of fingerprinting, so-called detection and attribution of climate change. And that's today a very important instrument to convince policymakers. When they tell you, oh, we're not quite sure, the glaciers come and go and the sun is making variations, so we're not quite sure whether carbon dioxide is really the important driver of the warming that we see in the last 50 years. Then you go back to detection and attribution, a statistical technique that combines observations and models to detect and attribute climate change. So you can actually say, what is the percentage of the warming due to the emission of fossil fuels? And that science in the last 30 years has evolved to the point where we can detect and attribute single events. Single extreme events can be attributed to the increase of carbon dioxide. And now you can imagine the significance of that. Because if you have a major flooding somewhere, people go to court and ask who's responsible for that. The science will give you the numbers. What the court decides is a different thing, but we scientists give the number. This flooding has been 30% stronger than ever because of the warming that we have experienced and because of the change in the precipitation patterns. Now, detection and attribution has also been important in the history of IPCC, from the first assessment report in 1990 to 2021, the sixth assessment report, and in 2013, the report that I had the privilege to lead with a Chinese colleague. We had this statement in there: human influence on the climate system is clear. Now, this is a statement that you would say, okay, that's a statement that I understand. It's probably a statement that was made by a journalist. No, it was a statement that the scientists said and proposed to the policymakers. The policymakers being delegates of all countries. They come together to approve this report. And so they have the privilege to actually raise their flag and say, oh, I'm not in agreement with this formulation. Please provide a different formulation. And in the end, you have to find a consensus. And, after our work, we were very happy that this very simple sentence found a consensus. The scientific facts were just overwhelming, so that even Saudi Arabia, Venezuela, the US, Russia, they could not say we do not accept, because the scientific evidence was overwhelming, thanks to this detection and attribution science that I was mentioning. That's sort of the nutshell of the summary. Human influence on the climate system is clear. Now, let's take a few minutes of the remaining time to look how the projections of global mean temperatures have evolved over the last 50 years, or even more. And it's remarkable what science was able to provide for those who listened at the time, or could have listened at the time. 1970, the name you already are familiar with, Suki Manabe and Wally Broecker. Wally Broecker was actually the first who coined the term global warming by publishing a paper in Science entitled, "Are We on the Brink of Pronounced Global Warming?" 1975, and these two individuals provided some estimate into the future how global mean temperature would evolve. And you see these two estimates here, made in the 70s, going out to 2010, an increase in temperature, global mean of about 0.6 degrees Celsius. Later studies by Jim Hansen, that is the individual that became famous because he testified before the US Congress. He had to testify and he said, yes, we see global warming. Very daring and courageous at the time, 1988. Manabe and Stauffer again. Manabe here with more detailed projections over the following decades to 2020. You already see that these models are able to also simulate some natural variability superimposed on the increase. And then we just go forward what IPCC as a consensus organization where all the policymakers agreed in consensus showed us projections in blue here from 1990 to 2007. And then we put that together. So IPCC was a little bit more conservative for some of the assessments. And then you look at the observations in black. And so again, this is really a story of success. And the success is not just haphazardly, but it's due to the physical understanding of the climate system. And we all know what this leads to. You see here the causes of that warming, the sources of carbon dioxide emissions from oil, gas, coal, and others, but also from land use change. Land use change is the word for deforestation, destroying the tropical and the mid-latitude forests. And so we go to projections. I don't want to dwell very long on that, but these same models that were used for the short term, you can also use for the long term out to 2100. But out to 2100, you need scenarios. You need assumptions that tell you, well, are we living or will we be living in a world of high fossil fuel intensity? Or will we manage to transform our society and energy system to renewable energies? The high emission scenarios are the business as usual scenario to which many lobbyists and interest groups want to stick because it's a business. It's called business as usual. Or other scenarios here where the emissions go down because we transform from fossil to renewable, and at some stage we may even reach net zero. You probably all heard about this goal of net zero. For the black scenario, that is somewhere here. For the sky blue scenario, that's just a bit after 2050. And we all know the heating should stay well below 2 degrees Celsius as per the Paris Agreement, but for all the scenarios that do not reach net zero in the 21st century, that heating will be above 2 degrees Celsius, and that means we will have an increasing risk of consequences as the temperature goes up. These are the instruments now. The models are much more realistic. You can ask Santos for more details because he is also using regional models, so we can even make statements about the consequences of anthropogenic warming in the Basque Country and other regions. So these models, as you have seen, contain the basic physics that have already stood the test of time. And so surface temperature change based on these models for the 21st century, I don't go into the details. September Arctic sea ice, it looks really grim. All of these scenarios go down by at least about 2/3 of present-day ice conditions in the Arctic, which means that this unique ecosystem in the high northern latitudes will change dramatically. Sea level is going up. The direction is clear. We just hope that no tipping point is reached that would actually follow this dotted scenario or this scenario here with the dashes. That is a scenario in which some of the parts of Antarctica would actually irreversibly melt. The same applies to Greenland. We cannot say at the moment where these tipping points are, but the higher the temperature is, the more likely they become. Regional differences will become more pronounced. Where it's hot, it will become hotter. The ocean will take up some of the heat, renders us a service, but that service is also limited in its potential. The same applies to precipitation, which is simulated by these models. You see intensifying colors as you go from 1.5 global mean warming to 4 degrees warming. This column here is clearly not compatible with the Paris Agreement. And so you see here, every degree of global warming accentuates the regional changes in temperature and precipitation. And for the final point that I want to make is a point about extreme events. We all know what it means to have heat waves. your fellow country citizens beyond the mountain, they know precisely what heat waves mean. 40 degrees and more in summer. You're blessed here in the Basque Country. But over there in the south, it's just terrible. It's these heat waves that will intensify and increase in frequency. That's just a picture from wildfires caused by a drying, caused by extended heat waves in 2021. And in the last IPCC assessment, also the heat waves were addressed. You see here, what used to be a 1 in 50-year event is now a 1 in 10-year event at 1.5 degrees warming, which is the first Paris goal, the more ambitious one. It's a 1 in, 8 times in 50 years. In 2 degrees, it's about 14 times in 50 years. But in 4 degrees world, this is the new normal. Practically every year will be as hot as a 1 in 50-year event now. In other words, people and ecosystems have no time to recover after such an extreme event, and the only chance of survival is adaptation. So since we don't know who is able to adapt, we better make sure that this last scenario will not materialize. But with business as usual, that will be the scenario that materializes. A very recent example that took everybody by surprise is the global sea surface temperature heating in 2023. So you see here the seasonal cycle of all years since 1982, with the mean here in the dashed curve from 82 to 2010, 30 years, and from 1991 to 2020, a bit warmer. That's every sea surface temperature from 60 south to 60 north, a huge area that is measured. And you see here in orange the behavior of this value over 2023, already outside from March 23 onward, outside anything that has been measured in the previous 40 years. 2024, the deep red curve, still far above, and only in July 2024, a couple of months ago, it came back to the value of 2023, but never back to sort of what we have experienced in the past 50 years. This is an extreme event by surprise. Some people have said the models cannot simulate that. That has taken us by surprise. Well, that's not true. We have looked at that just recently. It's a paper in preparation that shows that some of these simulations, of hundreds of simulations, actually do show such an event. So models are capable to also simulate surprises, and that's really a surprise, a big surprise. The question is, can we go back to more or less normal temperatures? And I don't think that will be the case. Anyways, I come to the take-home messages. Greenhouse gas concentrations have increased since the Industrial Revolution. Measurements have shown it. The altitude of effective radiative loss to space has increased, leads to a warming in the troposphere and a cooling in the stratosphere. The most telling fingerprint that it's carbon dioxide. So Clinton would say, it's carbon dioxide, stupid, and not the sun, and not something else. Measured changes in the Earth system over the last 50 years are attributed to the emission of greenhouse gases and aerosols. This attribution is a mathematical statistical technique that bases on high-quality observations and high-resolution models. With every half degree, extreme events will rapidly increase in frequency and intensity. And I'll just close with the sentence, limited climate change will require substantial and sustained reductions in greenhouse gas emissions. This was the consensus statement that I could approve after 4 days of negotiations. Every country was in agreement. But since then, since 2013, not much has happened. The only thing that has happened is that carbon dioxide concentrations have gone up still. And here is the last slide. For those who are not convinced yet, an even shorter statement: climate change is physics. Thank you very much.
Galderak egiteko sasoia da, zuen denbora da, eta baita ere nik eskertu nahi diet, Santi González eta Jon Saez ere bai, horrelako pertsona ospetsua, ikerlari ospetsu arlo desberdinetan ona ekartzeagatik. Eta beraientzako ere bai txalo bat.
You talked about how to transform the usage of fossil fuels to more renewable ones, but would you say that nuclear plants would be a sustainable way of getting there, like in the meantime, because we don't have the capabilities of doing those renewable energies right now?
Well, that's a very good question. I would doubt that we have not the capability, because renewable energies have been on a very steep increase. The situation that we have now with wind and solar and PV is that 10 years ago, nobody could have predicted that we will be 2024 at the percentage of energy production we are. But of course, it's a different way of producing energy in which we do not have a constant flow of energy that is available. And so for that, the primary energy source that needs to be expanded is hydropower. Absolutely. Now in Spain, I know that this is a particular challenge, but you have other alternatives for renewables, like wave energy, for example, and other forms of renewable energies. That being said, I say that nuclear technology should actually achieve the next level, where we have solved at least one problem, and that is the self-stabilization. In other words, where if something goes wrong in the reactor shuts down automatically and is less prone to human failure, which was the case in some of the accidents in the past. Now, the other fundamental issue is the issue of waste, and that has not been addressed in the last 50 years, unfortunately, although people promoting that technology were actually aware of it. And so we're still in the stage where things need to be resolved in this, I would say, extremely elegant way to produce energy. But that has been neglected. And the last point I should say is we simply run out of time, because you're all aware of the fact that if today Spain or Switzerland or another country decides to have the next power plant, nuclear power plant, it will take about 15 to 20 years until that power plant is on the net. That's just a process. It's a very complex technology, and it will cost likely 2 to 3 times more than was stated at the time people had to decide. Recent examples, Finland and the UK. Both these things happened there. It took much longer, and it cost much, much more money. And so the point is, we don't really have time for that. We cannot sit down and wait until that technology comes online. What we have to do is, with all our forces, renewables, and on the sideline, I have nothing against developing this technology in preparation of, say, 2050, to provide that remaining gap with nuclear.
But taking into account the waste it produces, would it be more effective to develop other technologies, such as, instead of fission, fusion technologies, like the hydrogen and deuterium?
Absolutely. Fission is sort of a lightning rod in fundamental physics, but if you have followed the fission the fusion research, you also see the huge challenges that are entailed with it. It's super interesting physics. So if I were younger, I'd love to, simulate hydrodynamic plasmas and stuff like that. That's extremely interesting, but it's a technology that is far, far from being mature to deliver energy in a positive way. The recent plant in America used 150 times more energy for the laser to ignite than the energy that could be drawn out of the very short fusion process that they could initiate.
Thank you.
So I want to make a question about the little ice age, which is just to put in context my question. The little ice age was a global event in which temperatures decreased between the 15th and 19th century. So as of today, historians cannot reach an agreement over why it happened. So can climate physics explain why it happened?
Absolutely, that's one of the research topics, and the causes of the Little Ice Age, this cooling, which was not really a truly global event, but it had a global significance. It didn't start right at the same time throughout the globe, but it was essentially a cooler period during the 15th to the 17th century. Caused primarily by an increased activity of volcanic eruptions, bringing a lot of dust into the lower stratosphere and aerosols that actually reduced the input of solar radiation. So that was one component with the water vapor feedback that was increased, but also changes in surface albedo in association with that helped to cool these temperatures down. And then you also have natural variability in the climate system where it can happen that you have a few decades of colder temperatures, which then lead to an increase, for example, in the alpine glaciers, which through the albedo feedback have a little effect also on the local temperatures. So I would say the question is not fully understood and solved, but we're on a good track there to pinpoint to volcanoes and also an element of solar variability that can be reconstructed through sunspot cycles that have data that go back right into that time.
Thomas, could you repeat, please, why when the troposphere heats up, the stratosphere cools down?
Can you repeat the question? Why the troposphere heats up?
No. Why when the troposphere heats up, the stratosphere cools down?
Oh, okay. Well, that was the first part of the lecture. Maybe you weren't here, but...
Yeah, but I didn't understand very well. Could you repeat, please?
Oh, okay. Well, okay, maybe I could show the slide. Well, it has to do with, if you look on the planet to the atmosphere from outside, imagine you're in a spaceship, and you look down to the Earth. Your line of view is blocked, okay? Down to about 5 kilometers, your line of view is not blocked. So you are looking at the atmosphere at an altitude of about 5 kilometers. At that altitude, the atmosphere has an annual mean temperature of minus 18 degrees Celsius. Now, if you translate the minus 18 degrees Celsius to an energy flow through the Stefan-Boltzmann law, you get at 238 or something watts per square meter. It's on the slide. The slides you can make available. And that is exactly the equilibrium temperature of the Earth. Now, if you increase the greenhouse gas concentration, you make the atmosphere less transparent. So in your spaceship, instead of being able to look down 5 kilometers to the altitude of 5 kilometers, you can look down only to 5.6 kilometers, which is 600 meters higher. 600 meters higher in the troposphere means about 3 degrees, means a radiative flux that is lower than the 238. If your planet loses less energy, it must heat up to come to equilibrium. You know, losing less energy, you heat up. And so that's the part of heating up until you reach the 18 degrees Celsius. And the 18 degrees Celsius, the minus 18 degrees Celsius is at 600 meters above that level. So that's the simple explanation. And for the stratosphere, it's the other way around because the temperature gradient there has a different sign.
Do you think that we can actually change, prevent climate change and global warming, or that there is no actual opportunity of this because people will say things but don't do anything at all?
Well, as you know, there are very strong forces to keep doing what they have been doing because they are earning money, and so that's the fossil fuel industry that sells you the fossil fuels, and all that depends on it. And unfortunately, in our industrialized way of living, a lot is dependent on fossil fuel. But there is no physical law that says that you need to use fossil fuels to lead an industrialized life or a life in a developed country. You need energy, but you know, there is no law that this energy must come from fossil fuels. And so, yes, there is absolutely hope, but without the political will, the will of the people, the will of the young generation, there will be no change. That's clear. And I can be very blunt. There are parties in countries, in many countries, who say, we have no problem. We do as we have done before because that's our business model. And so just remember, before COVID, there was this movement, Fridays for Future, probably also here in Spain. And that did change quite a bit. In Switzerland, I can tell you that example. In Switzerland, it changed the numbers of seats in the parliament. The right-wing parties lost, the Green Party increased. Just as a consequence of the Fridays for Future and the debate in the society and the consciousness, yes, we need to do something. That spirit was broken by COVID. They never recovered, and now, 5 years later, we have in Switzerland, and I'm only talking about Switzerland, we have a parliament again where those parties are in the majority that think we don't have a problem. And parties that do not consider the cost of climate change. Because the cost, others will pay the cost, not us today. So it's you who pay the cost. Who will pay the cost, your children. And so I think we really have a responsibility to act, and we can act. I'm absolutely convinced.
Beste galderarik? Jone galtzatu du leheno eskua,
Hello. You are in front of many students from probably different grades, like biology, geology, mathematics, physics, chemistry also. They are finishing their undergraduate studies in, let's say, 1 year, 2 years. Do you have any advice for people willing to make some research in this field from different backgrounds?
I think a lot will happen at the boundaries between these disciplines, at the boundary between physics and chemistry when it comes to thinking about storage possibilities for renewable energy. There is a lot of question when you ask about can we cover our energy need with renewable energies. You all know wind and solar is a highly fluctuating energy source, and so you need new and clever ways of storage. And the research at these boundaries between chemistry and physics, perhaps even biology, when you think about methane and stuff, is the way, or are the areas where I would emphasize that progress is coming from in the future. Very important to actually bring together the people who are dedicated from different angles of views. And I haven't mentioned engineering. At the end of the day, you also need engineers who implement these things, who actually then scale these new ideas up to industrial country-wise scales that can be used and make a difference.
Yeah, hello, I'm Sergio Enrique Faria from the Basque Center for Climate Change, former Collihutter student as well. And I have a question about a situation that we have in Spain, which is that there are some prominent climate scientists, some even with an IPCC badge, of course not from Working Group 1, who sometimes say in the media that climate modeling is something that should not be invested money in, because the physics is not understood and the money for research should go more into detection, measurements, local and policy advice, and so on. So what, as you worked in all those fields and you have experience in all of them, what would be your advice for the media which transmit this message for the general public and for the science decision makers in Spain about that? Thank you.
Well, I guess this statement is probably motivated by the question, what are the impacts of climate change? And so we really want to know the impacts. Now, how do you go about this question in a rational way? Do you go out and ask the question, the people with a questionnaire? How did you feel about the flooding yesterday and stuff like that, or the heat wave? Did you have a higher heartbeat rate, etc.? That's all good and fine. But what you want to do when you want to study impacts, you need a quantitative base for these studies. And the only solid base I know are climate models or meteorological models. It depends on the kind of extremes you want to study, because that's the initial information that you need for impact studies. And with impact studies, I mean the whole range of impacts, from physical to ecosystem to social and to future policy making. Because if you work in prevention, for example, without a climate model, you cannot do good prevention. And so those guys who say, we don't need climate models, didn't quite hear whether the argument was the physics is all clear or the physics is not understood at all. Well, that's even a more stupid affirmation. I'm sorry, but that's just a fact. The physics is not completely understood, but sufficiently understood to make, as I tried hard to demonstrate, it was already sufficiently understood in 1975 to make a projection over the next 30 years for a very simple variable, global mean temperature. But here now today in the 21st century, in the second decade of it, we would like to make predictions about the impacts of heat waves, the impacts of special weather patterns that evolve, that perhaps have never been here in the Basque Country. And only climate models and regional high-resolution weather models are able to provide that input for the research that then follows. So without that input, that other research, which then will receive more money, is futile.